Thanks for joining this session on Oracle Autonomous Database as a platform for data science and machine learning. I'm Mark Hornick with Oracle Machine Learning Product Management. And in this session, we'll explore key aspects of the Autonomous Database platform that enables you to produce data science and machine learning-based solutions. Let's take a brief moment to introduce Oracle Autonomous Database. Traditionally, each database deployment is more or less unique, where you need to build, secure, patch, and tune each database. And this is labor-intensive and doesn't scale well. With Autonomous Database, Oracle Database is reimagined for the cloud, revolutionizing data management by completely automating the full database management lifecycle, supporting mission-critical databases, and enabling you to innovate more, pay less, and ensure your data's security. But how do you innovate more? Well, by taking advantage of Oracle's converged database. In contrast, when you develop solutions using multiple single-purpose tools, you increase complexity from component interactions, as well as increase integration and maintenance costs. Further, end-to-end security, availability, and scalability can be inconsistent and limited by the weakest of your single-purpose tools. Oracle's converged database eliminates these issues by supporting multiple data types, analytics, and development paradigms in the same system. Oracle Autonomous Database not only places machine learning functionality at your fingertips, but also other essential technologies like spatial and graph analytics. And these are all in a single, secure, integrated platform, expanding data access and sharing while significantly reducing complexity. And these technologies are included in the core database at no additional cost. Now, to serve as a platform, though, we need to support the machine learning process. I'll touch on four main areas. Data understanding includes data exploration and visualization. It's key to understand what data you have, where it is, what it means, and its quality. Data preparation involves improving data quality, combining data from multiple sources, and deriving new predictors, or columns, and do this in a scalable and performant way, without requiring data extracts to separate analytical engines. Preparing data in Autonomous Database allows you to take advantage of query optimization, parallelism, indexing, and other database performance features. For modeling, we also want to avoid moving data, and that's why Oracle places machine learning algorithms directly in the core database software, just like it does for query processing and optimization. And for deployment, users need to quickly and easily include machine learning model results in applications and dashboards, using interfaces that mesh well with production systems. Autonomous Database supports deployment using SQL, R, Python, and REST interfaces, as well as built-in notebook functionality with versioning and job scheduling. So let's take a look at some of the tools available through Autonomous Database. On the data exploration and visualization front, as part of Data Studio, Autonomous Database provides tools supporting data load, analysis, insights, catalog, and sharing. In the catalog, you easily search for tables, views, analytic views, and cloud storage objects like Parquet or CSV files that are available in the data lake or data warehouse. You can see data statistics, lineage, and relationships between data objects. With data insights, you can quickly see patterns and anomalies in your data, explore relationships among data columns, all automatically derived using functions built into the database. Insights highlights unexpected patterns that you may want to investigate. Now, using the built-in notebook environment, you can take advantage of built-in data visualizations and use SQL, Python, and R language interpreters in the same notebook. You can take advantage of third-party Python and R packages using Conda environments and work directly with in-database machine learning functionality. Using Graph Studio, you can explore connections and relationships in data through intuitive SQL query extensions and leverage graph-centric analytics and machine learning algorithms. You can perform ranking, clustering, and path analysis. and detect anomalies, identify communities, and find new connections in your data. Using Spatial Studio, you can explore geographic and other spatial relationships in data with impressive visualizations and powerful spatial analytics. Manage different types of geospatial data, perform hundreds of spatial analytic operations, and use interactive map visualization tools. But let's turn our attention to examples of some business use cases you can solve using machine learning techniques in Autonomous Database. These include classification use cases, for example, to predict customers with high lifetime value, or those who are likely to prepay their loan or perhaps default on the loan. Other use cases may include predicting which vehicles need maintenance, or if a customer is likely to churn. We can apply regression to some of these to predict numeric outcomes, or forecast product demand, sales, or revenue. Time series forecasting offers another approach to these same use cases. Clustering helps with customer segmentation and document classification. Association rules can identify cross-sell and upsell opportunities, and anomaly detection is useful for transaction or claims fraud detection. And these examples just scratch the surface of what's possible. Oracle Machine Learning in Autonomous Database supports the machine learning techniques and use cases we've just highlighted, as well as others. For each of these techniques, AutoML provides several algorithms. And why do we have multiple algorithms for a given technique? Well, some algorithms are better at finding certain types of patterns in data than others. Also, different algorithms offer a greater degree of transparency to understand the patterns or insights that were discovered. And each has its own computational demands, meaning that some are faster than others. Let's take a closer look at these algorithms. The in-database algorithms keep data under database control. There's no need to extract data to separate machine learning engines. And this eliminates data access latency, maintains data security, and provides access to the most recent data. These algorithms are fast and scalable, enable batch and real-time scoring, and provide explanatory prediction details, so you can understand why an individual prediction is made. In-database machine learning models are first-class database objects. You can control access by granting and revoking permissions, audit user actions, and export and import models across databases. Once you build a model, it's immediately accessible through SQL queries. And as a database object, models are part of the database backup, recovery, and security protocols. All of this results in faster time to market of machine learning-based solutions. So how do we get an in-database model? Well, here's an example using AutoML for SQL to build a model that predicts if customers are likely to buy travel insurance, using the PL SQL procedure create model 2, which produces a model in your user schema. You can also build that same in-database model using R and Python functions. You'll notice that we use native syntax involving data frame proxy objects, so the data remains in the database. With a SQL query, you can score an individual customer using built-in prediction operators, as shown here, or perform batch scoring at scale. Such queries can easily be invoked from JDBC, Apex, or any other interface that enables SQL access to the database. And there are many other ways to build models and score data from SQL, PL SQL, Python, R, and REST. Check out the template example notebooks that are provided with Oracle Machine Learning on Autonomous Database. So, how would you typically go about building a machine learning model? Let's walk through the process to set the stage for discussing automated machine learning, or AutoML. As we said earlier, there are typically several algorithms for a given machine learning technique, like classification. It's unlikely to know which algorithm is best without trying a few. So we start with one, perhaps support vector machine. And using our prepared dataset, we build a model using the default settings, or what are called hyperparameters, and tune these settings to hopefully improve model quality. We compare each new model against the previous ones and select the best for this algorithm. And then we repeat this process with the next algorithm. This iterative and trial and error approach is expensive, both in terms of time and compute resources. It also requires that you understand how to tune the settings for each algorithm. And so, this is where AutoML comes in to simplify the modeling process by eliminating repetitive and time consuming tasks. This not only increases your productivity, but also makes machine learning more accessible to non experts, since you don't need to understand the algorithm settings. So let's look at the API functions of the OML Python API that support this. We start with algorithm selection, where the top algorithms are ranked. Here, SVM Gaussian is ranked highest. We next perform feature selection to find the columns that are most predictive of the target for our selected algorithm. Here, 13 columns are reduced to 9 for the previously selected algorithm. And then model tuning, which optimizes the settings for the selected algorithm and features. And after running these steps, you have a machine learning model in your database schema that you can use in applications and dashboards. However, not all users want to write code, so OML allows you to click your way to a model. Using the AutoML UI no-code user interface, you can build models with minimal input. Just specify your prepared data and the column you want to predict in what's called an experiment, and the tool does the rest. With a few clicks, you can generate editable starter notebooks. And these notebooks contain Python code using the OML for Pi API for building the selected model, including the settings AutoML chose to produce that model. You can rename models to make them easier to recognize, as well as deploy them to OML services for use from REST endpoints. With OML services on Autonomous Database, you can manage and deploy machine learning models using a REST API for flexible application integration. OML services enables key elements of MLOps, supporting model management, deployment, and monitoring. The model deployment and management services enable you to deploy in-database models from both Oracle Database and Autonomous Database, as well as ONNX format models produced in other environments. Scoring using OML services is optimized for streaming in real-time applications, meaning it's fast, with millisecond response times. OML services also enables data and model monitoring. Data monitoring provides insight into how your enterprise data evolves over time, and this helps to maintain data quality standards, separate from or in conjunction with machine learning. Now, model monitoring involves identifying when a user-specified model metric, like accuracy, significantly changes, or the distribution of predicted values deviates too much from initial values. And this may signal the need to rebuild your model. And unlike other tools that require provisioning a VM for 24/7 availability, OML services is provisioned and maintained as part of Autonomous Database, so you pay only the additional compute when producing actual predictions. So let's turn our attention now to R and Python. Deploying solutions using R and Python can introduce several challenges for application developers and production engineers, including separately managing these analytical engines. OML for R and OML for Pi support native interfaces to the in-database algorithms, but they also support embedded execution to allow you to deploy native code using database-spawned and controlled engines. This code may also use third-party packages from the R and Python ecosystems. Embedded execution enables invoking user-defined R and Python functions from SQL and REST APIs, which can greatly simplify using R and Python in your applications, especially when those applications aren't written using R or Python. An additional benefit is the ability to easily specify data parallel and task parallel processing. For example, you can store a native Python model in the database and use it to score large volume data across multiple Python engines concurrently that are spawned and managed by the database environment. Each engine scores chunks of data automatically provided by the database, and you can access the scores produced from all engines as a single database table. If you ask your favorite chatbot what the top 10 enterprise requirements for data science and machine learning are, you'll get a variety of responses, as you'd expect. However, they tend to generally agree on many such requirements as shown here. Autonomous Database supports each of these, from scalability and security to AutoML and cost effectiveness, to be your platform for data science and machine learning. I'll just elaborate on a few of these. Data security goes beyond just data. It also includes many of the various artifacts derived from data, like machine learning models, and even SQL, Python, and R scripts. In-database models are first-class database objects and automatically benefit from the same database security features. Models produced using native R and Python packages can also be managed directly in the database. Integration means less work for administrators and greater ease of use for data science teams. With Autonomous Database, all the machine learning, spatial, and graph components are ready for use. They are automatically patched and updated as new features become available. One aspect of machine learning is explainability. That is, the ability to interpret and explain the predictions made by machine learning models. To enable transparency and regulatory compliance, in-database models provide explanatory prediction details to understand which factors most contribute to individual predictions. And lastly, let's highlight cost effectiveness. If multiple technologies are used to support a solution, costs involve not only acquiring those tools with ongoing support, but installing, configuring, and patching them across the enterprise. In contrast, leveraging a converged database like Autonomous Database, where such tools are included with the core product, greatly reduces costs and simplifies operations. So, for more information and to get started using Autonomous Database, and OML in particular, check out these resources. To get hands-on experience with Autonomous Database, see Oracle Live Labs workshops. One of the links here is for Oracle Machine Learning Fundamentals, which covers several of the OML-related components we've talked about. So thanks for joining me to explore Oracle Autonomous Database as a platform for data science and machine learning, and enjoy the rest of the conference.